Why is fire hot? The hidden science inside every flame. Fire asks a strange question every time you light a match. If fire is the thing that gives off heat, why does it need heat to exist in the first place? Strike the match too gently and nothing happens. Warm a piece of wood just a little and it stays cold. But cross an invisible threshold and suddenly a tiny spark becomes a dancing flame, hot enough to melt metal or power a rocket. It almost feels as if fire creates energy out of thin air. Yet one of the most familiar things on Earth is hiding a remarkable secret. Fire isn't making energy at all. It's revealing energy that was there all along. For thousands of years, people believed fire was one of the basic building blocks of nature, alongside earth, air, and water. That made sense. Fire looked like its own mysterious substance. It could appear, grow, move, and disappear. It seemed alive. Modern science tells a very different story. Fire isn't an object you can hold. It isn't made of heat, and it isn't a special state of matter floating above the wood. A flame is actually a fast-moving chemical reaction. What you're seeing is a cloud of incredibly hot gases, glowing particles, and light produced as fuel reacts with oxygen. But that only raises an even bigger question. If fire is just a chemical reaction, where does all that incredible heat come from? The first clue appears before the fire even starts. Imagine trying to light a campfire. You rub two sticks together or strike a match. That first burst of heat isn't optional. Without it, the wood simply won't burn. Scientists call this the activation energy. Think of it like giving a heavy boulder one hard push before it rolls downhill. The push doesn't power the entire journey, it simply gets the process started. Once the fuel becomes hot enough, something extraordinary begins happening at a scale far too small to see. The molecules inside the wood start breaking apart. Oxygen molecules in the air collide with them millions upon millions of times every second. New combinations begin to form. At first glance, that sounds confusing. Breaking chemical bonds actually requires energy. So shouldn't bonds have to be broken, the reaction cool everything down instead of heating it up? Here's the twist. The real source of the heat isn't breaking the old bonds, it's forming new ones. Imagine taking apart a wobbly stack of building blocks. It takes effort to pull it apart, but then you rebuild the blocks into a much stronger, more stable structure. That new structure sits at a lower energy level than the old one. The same thing happens during combustion. The carbon and hydrogen atoms in the fuel rearrange themselves with oxygen to create new molecules, mainly carbon dioxide and water. These new chemical bonds are more stable than the original ones. As the atoms settle into these lower energy arrangements, the extra energy has to go somewhere. It escapes as heat. Some of it also becomes light. That's why fire feels hot. Not because flames magically create energy, but because atoms are falling into more comfortable, lower energy arrangements and releasing the difference. It's like watching billions of tiny springs snapping into a more relaxed position all at once. That hidden chemical energy becomes the thermal energy warming your hands beside a campfire. And here's where things become even more fascinating. The heat released by those first reactions doesn't simply disappear into the air, it heats nearby fuel. That hotter fuel reaches its own activation temperature. It begins reacting with oxygen as well, releasing even more heat. The process feeds itself. As long as fresh fuel and enough oxygen remain, the chain reaction continues. This is why a single match can eventually ignite an entire log. The match doesn't contain enough energy to burn the whole piece of wood by itself. It only supplies the first push. After that, each reaction provides the heat needed for the next one. But if every fire works this way, why don't all flames look or feel the same? Because every fire is solving the same chemical puzzle under different conditions. The type of fuel matters. The amount of oxygen matters. How well the gases mix matters. Even how quickly heat escapes into the surroundings changes the result. A typical wood fire may reach roughly 600 to over 1100 degrees Celsius, while carefully controlled industrial flames or specialized fuels can burn much hotter. Size isn't always the answer either. A giant yellow flame may actually be cooler than a much smaller blue one. That surprises many people because bright yellow flames look more intense. But much of that yellow glow comes from tiny soot particles becoming hot enough to shine. Blue flames usually indicate more complete combustion with better oxygen mixing, and they are often hotter. The hottest part of a flame isn't always where your eyes expect it to be. Even the flame itself isn't quite what it seems. When you look at a candle, you're probably imagining you're seeing fire. In reality, most of what you're looking at is glowing hot gas mixed with microscopic particles. Fire isn't a solid thing floating in space. It's a constantly changing cloud where countless chemical reactions are happening every fraction of a second. Every flicker marks molecules colliding, breaking apart, and rebuilding themselves into something more stable. The same basic chemistry appears in places far beyond a fireplace. The engine inside a car works by carefully controlling combustion to push pistons. Jet engines produce enormous thrust by rapidly burning fuel in flowing air. Rocket engines rely on combustion powerful enough to escape Earth's gravity. Scientists study flames to design cleaner engines, safer buildings, better wildfire predictions, and more efficient industrial furnaces. Even today, the turbulent behavior of flames remains an active area of research because the chemistry becomes incredibly complex as gases swirl and mix. Nature has been using combustion for millions of years as well. Wildfires may look destructive, but many ecosystems evolved alongside them. Some plants actually depend on periodic fires to release seeds or clear away competing vegetation. In those environments, fire isn't just an accident, it's part of the cycle of life. Then comes perhaps the most surprising connection of all. Your own body is performing oxidation right now. Every breath you take supplies oxygen. Every meal provides fuel. Inside your cells, enzymes guide countless tiny oxidation reactions that slowly release chemical energy. It's remarkably similar to what happens in a flame. The crucial difference is speed. Fire releases stored energy almost instantly, producing visible flames and intense heat. Your body releases that energy through thousands of carefully controlled steps, preventing you from bursting into flames every time you eat breakfast. Even rust belongs to the same family. When iron combines with oxygen, it's undergoing oxidation too. The process is simply so slow that the energy leaks away gradually instead of appearing as fire. In a sense, rust is an incredibly slow fire. That idea changes how ordinary flames look. A campfire isn't creating energy from nowhere. Much of the energy inside the wood originally came from sunlight.
Trees captured that solar energy through photosynthesis and stored it inside chemical bonds over years or even decades. When the wood burns, those atoms rearrange themselves into more stable molecules, releasing a portion of that stored energy back into the world. The next time you watch a candle flicker or stare into a glowing campfire, you're not just looking at something hot, you're watching billions of molecules racing towards lower energy forms, turning invisible chemical potential into warmth and light, and revealing that one of nature's oldest mysteries is really a story written by atoms.